I'm going to run through a couple of projectile motion examples. I'll do separate videos for them, and I'll start with an easier one. So projectile motion example. The easiest form of these looks like this. I'm going to start here. I'm going to take a ball and kick it. We'll start with a velocity of, this way we'll go 20 meters per second, and we'll put this thing at an angle of 53 degrees. I want to know, where does the ball land? And I would like to know, how high does the ball go? So two different questions, and we can answer them in either order. We can pretty much always answer them in different orders. I'm going to try this one just the way that it's written. So this ball is going to go up. We don't have air resistance, and it's going to come down and hit some spot. I'm going to make a couple of labels right off the beginning. I'm going to call that my x-axis, and this is my y-axis. So I would like to find, that means right here is the origin. I would like to find x final. That is, where does the ball land? When I'm doing this, I'm looking at this as a projectile motion question, and I can only do so much with it. I have to look at the moment this problem starts, the moment right after I've kicked the ball, and the problem ends the moment right before I hit the ground. While my foot's in contact with the ball, there's an extra force going on because of my foot. When the ball strikes the ground is exerting a force on the ball. So what I can do is look at the portion that is pretty much from right here to right here. And I'm going to say that that will represent my motion well. So projectile motion means I'm going to have to do kind of two separate problems. I need to keep track of the x and the y. What I know right from the start is that as soon as the ball is in the air, my acceleration is going to be straight downward. I'm going to need to take this initial velocity vector and break it into components. So let's do that. Here is the horizontal component. Here is the vertical component. This is going to be my v initial y, v initial x. I'm going to do this using basic trig, right? I have this right triangle, and I'm going to say v initial x is going to be v initial times the cosine of 53 degrees. So 20 times the cosine of 53 degrees is going to be 12 meters per second. V initial y is going to be v initial times the sine of 53 degrees, which comes out to be 16 meters per second. So there's that. Now I'm going to set up my table. So I'm going to say x initial, x final, v initial, v final, acceleration, and time. Here's my x direction. Here's my y direction. When I'm plugging into my y direction, I recognize that x initial is going to become y initial, but that's pretty easy to work past. So there's my table. Now I'm going to start filling in values where I can. First, x direction. I know my initial position 0. My final position I don't know, but it is what I'm trying to find. My initial velocity in the x direction, that's 12 meters per second. I found that by breaking my vector into components. I'm going to skip v final for just a moment. My acceleration in x. Once I'm in the air, there is nothing acting horizontally. The only thing that's acting on the ball once the ball is in the air is gravity. Gravity pulls straight down, so it does nothing horizontally. I don't know how long the ball is in the air. I'm not asked to find it, so I'll label it with a question mark and recognize that I might not have to find it. My v final. If my acceleration is the rate of change of velocity and my acceleration is 0, then that means my v final is going to be equal to my v initial, so that's going to be 12 meters per second. Onward. Y direction. My initial y position is 0. My final y position, I'm going to hit the ground again, so that's also 0. Now this is a special case because I'm starting and ending from the same height, but it's a special case that's really going to represent something like 30% of the problems that you actually do. So special, yes, but not uncommon. V initial in the y direction is 16 meters per second. I'm getting that from my parabola, from breaking this into components. My acceleration in the y direction, that's going to be from gravity. There's my negative 10 meters per second squared. I still don't know the time. My v final. Now, because I am going up and then coming down and landing at the same height, I know that my v final is going to end up being negative 16 meters per second. For right now, I will do this. I'm going to write it in a different color because this is a special case. It comes because these two are equal. It's not going to be the case all the time, so I don't really want to get into that habit. I'm going to write it in a different color and then kind of not use it because I think it's going to be an important thing to be able to do these problems without necessarily assuming that you can do that. Now I will write my kinematic equations. Done with my picture, and I can write my equations. And that'll be my starting point. What I know, you remember when we did pursuit problems, how there was some kind of a common ground that we could work with? That's going to happen with projectile motion problems too. I know that however long I'm in the air in the x direction, that's how long I'm in the air in the y direction. So these, even though I don't know what they are, I do know that they're going to be the same as each other, and that'll be helpful. Okay, maybe I can start with the x direction. That is, after all, where my unknown that I'm trying to solve is, so it's as good a place to start as any. When my acceleration is 0, equation 2 becomes v final equals v initial. True, but not helpful. Equation 3 becomes v final squared equals v initial squared. Again, true, but not helpful. As soon as my acceleration is 0, I know I want to use equation 1 because it's the only one that has anything useful in there for me. So I'm going to start with equation 1. X final, hey great, that's what I'm looking for, equals x initial plus v initial t plus half a t squared. I don't know my time, so I guess I'm going to write that in a different color. I will write that in red because I don't know what it is. I can cross off my x initial because that's 0. I can cross off this last term because my acceleration is 0. So I get x final equals v initial times time. There are two unknowns in this equation, x final and t, and I cannot solve for two different unknowns with only one equation. I already said that equation 2 is useless to me and equation 3 is useless to me, which only leaves equation 1. I can't really do anything else with it. So as far as my x direction information goes, I am out of cards to play. I'm going to have to move on and look at the y direction. If I'm going to be messing with y direction, I want to make sure that I can differentiate these later. So I'm going to say this is a v initial x, just to be able to keep track of it later. Y direction. I used equation 1 for x, so I would kind of like to use equation 1 for y because I know I'm going to have the same couple of variables. So here we go, y final, y initial, v initial t, half a t squared. I can again cross off what I can cross off. It's that one and that one. And that leaves me with 0 equals v initial t plus half a t squared. I can solve this thing. T is going to be negative 2 v initial over a. If you are unsure of getting there, I'm actually just going to write the steps in between on this one. So I am subtracting v initial t from both sides. That gives me negative v initial t equals half a t squared, and then I am canceling out a t. Negative v initial equals half a t. I'm going to multiply by 2. And then I'm going to divide by a. And that leaves me with t equals negative 2 vi over a. Well, that's great. I have all those variables. So I'm going to plug in negative 2 times v initial divided by the acceleration. This is y direction stuff, so that is a v initial y. And I can put those values in to remind myself, but I'm just working on this far right column. So all of my stuff is staying there, which is helpful. It might be a good thing if you need it to take the x direction equations and stick them over here, and the y direction equations and stick them over here, and just treat the whole problem as separate. I'll try that in the next video. Here we go. Negative 2 times 16 is negative 32 divided by negative 10 is positive 3.2 seconds. Once I have that, so I found my time. Now I can plug that in here, 3.2 seconds. I like to fill out the remainder of the table because when there's a part B to a question, then it's a helpful thing to be able to just look at it and say, hey, I have this information now. I was looking for x final. Glad I put a star next to it. These problems get long. I have this equation right here that I had been working on. And now that I've got this t value, I can solve. V initial in x was 12 meters per second, multiplied by the time, 3.2 seconds, and I get that my x final is going to be 38.4 seconds, or meters. And I have just found where I land. I can fill that value in too. But being that it was the last thing, that's good enough. Now, I was also asked, how far does this thing go? Or how high does this thing go? To do that, I'm going to use a different table. Reason I'm going to use a different table, this one was for the full trajectory. I am not looking for the full trajectory anymore. I'm looking for just to the max height. So that table was good to land here. But now for part B, or for question 2, I am looking at this location. This is question 1. This is question 2. I'm looking at that location. So I'm going to make a new table. Let's see. My y initial is going to be 0. V initial, that's still, I calculated that before from breaking into components, that's still my 16 meters per second. V initial in x is going to be 12 meters per second. X initial is going to be 0. Let's see, I know that one. I know that's still 12 meters per second. I don't know the time. Kind of. I know my acceleration in y is going to be negative 10 meters per second squared. Let's say I don't know this one. I don't know x or y final, but that's the thing that I'm looking for. I do know that my v final in the y direction is going to be 0. Vertically, if it's positive, I'm still moving up. If it's negative, I was moving up at some point. I'm coming down from somewhere higher. So it's got to be 0 at that maximum height. Now, just like before, where I gave you some different values and said, yes, I know what these are, but I'm not going to use them yet, I'm going to do the same thing here. What I found before was that for the full trip, it was 3.2 seconds. Because this one starts and ends at the same height, that means I'm going to have 1.6 seconds. I'm going to have exactly half the time to get to the top. But I'll put an asterisk by that one. That's a special case because they start and end at the same height. I also found that I go 38.4 meters for the whole trip. So I'm going to be at half that. But again, I'm not going to use that just because it's a special case situation. And it can be a nice shortcut, but it's not a great way of learning how to do the problem. I'm looking for y final, and I'm going to grab these same equations. I already wrote them once. I'm going to grab these same equations. I'm looking for y final, so I would like to start with the y direction if I can. I'm again pretending that I don't know this time just yet, but if I don't know the time and I'm looking for y final, I can use equation 3, and that'll work. Equation 3 says v final squared is v initial squared plus 2a delta y. I also know that thing is 0. So I can solve for delta y. And actually, I have all these variables. I don't need to use any of the x direction things. I started using just y because that was where the variable I was trying to solve for was. And I thought, man, it'd be nice if that just works. And it does. So I'm going to go negative 16 meters per second squared over 2 times negative 10 meters per second squared. 16 squared is 256, over 2 is 128, divided by 10 is 12.8, and my minuses cancel. I'm going to go 12.8 meters into the air, and I've answered both my questions.